Today's lecture, we're going to look at exponentials and logarithm equations. So last few days, we talked about those properties and did examples to make sure we understand how to use those properties. Now we're going to look at how to solve exponentials or logarithmic equations using those property that we learned from before. So we have several different types of problems that we're going to deal with. This is the first types of exponentials that we're going to deal with. So this example 1 will show you all types of exponentials where you can make the same base. Okay, so example 1 will show you all of the example where you can make same base. So for example here, 3 and 81, I can make a same base. 3 to the 4th exponent is 81, so I can make a same base. This one, 27 and 9, I can make a same base as 3, right? 3 cube and 3 square. Here, 25 and 1/5, I can make a same base of 5. This is 5 square, and this is 5 to the negative first exponents. So this example 1, if you have exponential equation given, and if you can make same base, this is the method you're going to use. Okay, so long as you can make a same base, that's how you're going to start it. We know 81 is same as 3 to the 4th exponent. Once you made a same base, so this is same base right here and there. Once you have same base, drop the base, just let the exponent equals to each other. So I'm going to have only exponents, 2x minus 6 equals to 4. Long as you have a same base, just let the exponents. So this exponent right here equals to this exponent. You have the same base already. So then when we solve for x, we add both sides by 6 and then divide by 2. So if x is 5, then both power here and here will be 4. So if you wanted to check, you could say 2 times 5 minus 6 should be 4, right? So then that's 10 minus 6, that's 4. So this way you get 3 to the 4th exponent equals to 3 to the 4th exponent, right? So only way that this 2 side will be equals to is when x is 5. And do the same thing. So the next example, 27 on the base, we know that's 3 cube. And then you had x plus 3 on top of it, right? And then 9 is 3 square. And we have x minus 1 on top. And when we simplified our exponents, this is the same as 3 to the 3x plus 9, right? Because you're distributing 3. And when you're distributing 2, your exponent become 2x minus 2. Again, if you have a same base, now drop the base and let the exponent equals to each other to find out what x is going to be. This is linear, so put the number with the variable together on one side, without the variable on the other side. So that gives you x on the left, you get negative 11 on the right. And again, you can check your solutions. So when you replace 11, here you get negative 11 plus 3. And then when you replace negative 11 here, which is negative 11 minus 1, is going to be negative 12. So 9 to the negative 12's exponent will be same as 27 to the negative 8 exponents. And you can take that from your calculator. So your solution on this one is going to be negative 11. Let's try the other one. So make it same base. If you can make it same base. So this is 25, so it will be 5 squared. You get 4 minus t. And 5 to the first exponent is, 1 over 5 is 5 to the negative 1 exponents, right? Negative makes your base flipped, so plus 1. And then simplify your exponent by distributing one term into two terms. So you get 8 minus 2t exponents. And this is going to be negative 3t minus 1 exponents. Once you have same base, drop the base. Let the exponent equals to each other. And solve for t. So you wanted to put number with the base together. Number without the base, a variable together. So that gives you positive 1. This is negative 9. That will be your t. If t is negative 9, the left side of the t will be same as the right side of the t. Next example of exponential is when you cannot make it same base. So for example, the first one right here, this base is 7 and this base is 60, and you cannot make a same base on this problem. All this example you're going to see in example 2, you cannot make a same base. So then what do we do, right? This is when we're going to use logarithmic to help out to solve this exponentials. So what I'm going to do is I'm going to multiply both sides by logarithms, and especially natural logarithms. The reason I'm using natural logarithm because sometime your problem will carries value e like this one, right? And if I have a natural logarithm of e, then that's going to be equals to 1. So sometime using natural logarithm helps. So instead of using log 10 and natural logarithms on different problem, I will just use the natural logarithm for everything. So I'm going to multiply both sides by natural logarithms. So this side, I will multiply by natural logarithm, and I will multiply natural logarithm by the other side. Then what I have is ln 7x equals to ln 60. The reason I multiply natural logarithm is because use the power rules. You see this power right here because now this is the logarithmic expressions. This power, I should be able to bring it down. I can make this power into the multiplications. So then I can rewrite this as x times natural logarithm of 7 equals to natural logarithm of 60. So once you bring your variable into the base, now you just need to isolate this, right? You isolate x by multiplying or dividing both sides by natural logarithm of 7. Then your x is equals to ln 60 over ln 7. And when you replace that into a calculator, you will get somewhere close to 2.1. I'm going to try that again with example B. So I'm going to, if I cannot make a same base, I'm going to multiply both sides by natural logarithm. why do I multiply by natural logarithm? So I can bring my exponents down into base. So then I get x times ln 10 equals to ln 120,000. And then in order to isolate x, you divide both sides by ln 10, right? Where your x should be, it will come out to decimal on your calculator where it's close to 5.08. Same thing with C, it's just that before you decide to multiply, you need to make sure you isolate one side with only exponentials. Like this two example right here, right? The first two example, only left side, I have only term with exponents, right? Only term with exponents. I cannot have anything else, addition or subtraction attached to it. So if I have addition and subtraction attached like this one, the first thing I wanted to do is get rid of them. So I will have only the exponent terms on one side. So I will subtract both sides by 820. Then I will have 10 to the 5 plus 2x equals 2. The other side, when I subtract 820, I get 48,780. And once it's one side only exponents, that's when I'm going to multiply both sides by natural logarithms. And if I multiply both sides by natural logarithm, then I can bring my exponents down. If you have more than one term of exponents, you need to make sure you use the parentheses. And then you need to open the parenthesis, right? Because your x is inside of the parenthesis. So when you distribute ln 10, you have 2x times ln 10 equals to ln 48,780. And you wanted to move everything but your x. So your x is right there. So I wanted to get rid of the addition first. So you have 2x natural 10 equals to ln 48,780 minus 5 natural 10. And then you can isolate x by dividing 2 times ln 10, right? So this 2 and 2 cancels out, ln 10 and ln 10 cancels out, right? So you need to do the same thing on the other side. Divide by 2 times ln 10. Then you have only x on the left side, and the numerator will be ln 48,780 minus 5 times ln 10 over 2 ln 10. And this, you will get somewhere close to negative 0.156. And you need to make sure when you're inputting this solution into the calculator, you wanted to make sure you have a parentheses. So you need to use the grouping for the numerator. Otherwise, you're not going to see the difference of the numerator and denominator. So you open the parenthesis, and when you plug in natural logarithm on the calculator, they will have a parenthesis automatically. So make sure you close before you do the subtractions. And 5 times ln with the parenthesis, and you need to have another parenthesis close, right? This is going to be parenthesis. and then do the division sign, and you need to open the parenthesis one more time and 2 times ln 10 with close parentheses. So if you don't use this large parenthesis differentiating numerator and denominator, you will not get the right solutions. So be careful with that. Let's look at the next example. This one right here, we have exponents on the right side this time. And I wanted to isolate the term with exponent itself, so this is going to be it, right? E to the negative 0.4t. So 18,000 is not under the exponent, so I wanted to get rid of that one first. It means I'm going to divide both sides by 18,000 to isolate the exponents terms on one side, right? Then this 2 cancels out. This side right here is going to be, all the 0 cancels out, so it will be 2 over 18, which is 1 over 9. And the other side is going to be e to the negative 0.4t. And now I'm going to multiply both sides by natural logarithm so I can bring my exponents down, right? I wanted to bring my exponents down. And then what do I have? I have, this is one term, so I don't need parentheses. Natural logarithm of e equals to ln 1 over 9. And one thing we know is natural logarithm of e is equals to 1. Why is that? Let's look at that. We have natural logarithm of e is equal to log e. And when small base, larger base, same, we know that's equals to 1, right? So we should be able to get rid of ln e into 1. Then now I have natural logarithm of 1 over 9 equals to negative 0.4t. Now I should be able to isolate t by dividing both sides by negative 0.4. So let's divide both sides by negative 0.4, and your t is equals to natural logarithm of 1 over 9 over negative 0.4. So that is close to whatever numbers, right? That's going to be. You try it out and write down the solution, what that's going to be. If you're in my in-class, this is going to be okay as the solutions. But when you're doing your exam online, they will ask for the decimal values. What about next one, e? We have 4 to the 2x exponent minus 7. So here we have two of exponents. So this other side is also exponents. So in that case, I don't have, well, it's already one side with only exponentials. So what you can do is multiply both sides by natural logarithm. And then you can bring your exponents. And don't forget, when your exponent is more than one term, you wanted to use the parentheses. And when you open the parenthesis by distributing one term into two terms, right? Your one term you distribute into two terms, and you do that to other side. Then you end up getting 2x ln 4 minus 7 ln 4 on the left side. Right side, 3x ln 5 plus 1 ln 5. And you see there is 4 terms, but 2 term with variable and 2 term without the variable x. So you wanted to put it together. So you wanted to put number with the value with the variable x one side. So positive 3x ln 5 become negative 3x ln 5. And the other side without the variable. So it will be 1 ln 5 plus 7 ln 4. And from this 2 terms on the left side, I can factor x out because both terms have x, right? So I can factor x out. When I factor x out, then I will have 2 ln 4 minus 3 ln 5 remains. And same thing on the other side. And we will divide both sides by 2 ln 4 minus 3 ln 5 to isolate x itself. So then your x will be that. And when you don't forget, you wanted to put parentheses to differentiate the numerator and denominator on the calculator, right? And the calculator automatically opened the parentheses for the value of the natural logarithm. So you need to put all this to the calculator. Then your x should be this one. I already figured it out. And so I can give you the value, which is going to be negative 5.50. What about this one, f? I need to isolate e to the 2x exponent by itself. Always one side of equations isolate by exponential form itself. So I need to get rid of negative 5 by adding 5. Then I will have e to the 2x exponents equals to, add 5, I get 63. And when I multiply both sides by natural logarithm to bring down the exponents, this is what I have, and I know that ln e is another 1. So basically I have only 2x on the left side. In order to solve x, I divide both sides by 2. And then I get x equal, I already got this, right? Or close to whatever the value of the decimals. Example 3 is last types of exponentials. So these exponentials, as you can see, you have 3 different terms. Once you simplify, you have 3 terms. One have to be constant, where you don't have any exponents. The other 2 have exponents, but this exponent have to be double. So this is x, and the other one have to be 2x, right? When this exponent is double and you have 3 terms, and the third term don't have exponents, constants, then you can always use the substitution method. Like this is going to be similar as the quadratic equations with the 3 terms. So something like having x squared plus bx plus c terms, right? When you factor this, you get x times x and whatever other values and all these other signs, right? So this is the method we can use. So when we're factoring, these first two values always come from the second term right here, right? X times x makes it x squared. So same thing when you're factoring this one. So when you're factoring these three terms, the first two value will be e to the x exponents. And I got that from the middle terms, right? Middle terms. And when you multiplying those two, you end up getting e to the 2x exponents, right? And then the sign of your constant is negative, means that you're going to have two different signs, right? So one with the positive, the other one with negative. So let me write that down. One with the positive, one with the negative. And the factor of 36, it gives you addition of 5 is what we're looking for. Factor of 36 factor, it gives you addition of 5. That's going to be 9 and 4. And since we have to make it positive 5 when we're adding it, 9 must be positive. And 4 will be negative, equals to 0. So don't forget, we were doing it like if we have x squared plus 5x minus 36, right? If we factor that, it will be x times x plus and minus factor of 36, it gives you 5 is 9 and 4, right? So exactly same as this one. It's just that instead of x and x squared, you have e to the x exponent and e to the 2x exponents, right? That's the only thing difference. That's what this value is different than your quadratic. So then once you factor, you let the each factor equals to 0. And solve for each factor. So subtract 9 and multiply both sides by natural logarithm. And then you solve. But this one, we cannot solve any further. Why? Because you have negative in the larger base. You cannot have negative in a larger base. So, and this one is equals to 1, right? But still, you have x equals to natural logarithm of 9. And when you plug in this into the calculator, you will get undefined. So this one, you get no solution because the larger base cannot be negative. The other one, when you add 4 and multiply both sides by natural logarithm, that will be 1. So x is equals to ln 4 is what you're going to get. And if you want exact value, input it into calculator, you get 1.39. Right? So either one will be okay. On a computer system, they will probably ask for exact decimal values. Okay, so then let's try another one just like that. Remember, if you have 3 terms, so let's look at this one again. 1, 2, 3 term. 1 is constant. The other 2 exponent is double. We can always use the factoring trinomial method, right? So when I factor this, my first value will be value from the middle term, e to the x exponents. Remember, quadratic, when we're factoring x times x, it comes from the middle terms. So we will have e to the x exponents. And you have addition sign. Addition means you're going to have same sign. The same sign must be this negative, right? So it will be minus minus. And then you're going to look at constant again, say a factor of 3, it gives you addition of 4. That's 3 and 1. You only had one options. So once you factor, let each factor equals to 0. And solve for x. And multiply both sides by natural log. And we know this is equals to 1. So x is equals to natural logarithm 3 for one solution. The other one, let's see if I have solution for that one. You multiply natural logarithm to bring down the exponents. And ln e is 1, so x is equals to ln 1. That's another solution. So long as you don't have a larger base, not negative, you should be able to keep it as solution. If you get negative larger base, like the other one right here, this one, if larger base become negative, make sure to exclude that. That will give you undefined solutions.